Okay, so we are talking about context free grammar. So just to recap, so it consists of 4 tuple V, T, P and S, where V is the finite set of variables and T is also finite set of terminals, or we can say alphabets in our automata terms. It is a set of alphabets which is finite, and P is the productions. So, P will be of this form like this, set of all such rules A going to alpha, where A is a variable and alpha is a string which consists of the variable and the terminals. Okay. So, all such production rules, all such productions is the P, that is the productions, and this S is the a special variable which is a coming from V, which is a start variable we can say. Okay. So, this any such 4 tuple is called context free grammar. Now, in the last class we have defined the derive. Say if say let us take an example. Suppose we have a grammar like this. So, we have only one variable and say we have a we have few terminals plus into bracket, this bracket, ID. So, this we have seen in the last class. So, what is E? E is the only variable. So, our S is also E. Now, what is P? P consists of this. E is going to E plus E, or so this way you can write, we have seen E bracket or ID. These are the rules. Okay. Now, we can take some derivatives like E is going to, we can take any one of these, say E is going to bracket E, this derivative. Then we can take this E is going to E plus E or E star E, star means into we can say. Then we can say this E is going to ID. Then we can not equal, this is the derivative derive. Now, we can say this E again is going to ID star ID. Okay. So, this is the, so if we take this one, so this is derived from this, but not with the one step, but this E is derived from, this is derived from this by one step. So, we can write E is derived, this is derived just one step G. Okay. Now, this is derived in 3 step 1, 2, 3. So, we can say 3 we can write here. This is 4 step, or in general we can write star G. G means the grammar rules. So, by this rule we are deriving this. This star means more than one step we can derive this from the starting variable. So, that is the meaning of star. Now, based of this star we can define the language of this grammar, or we can say the language generated by G. Suppose we have a G, so what do you mean by language generated by G? So, this is denoted by LG. LG is the set of all strings of terminals. This is coming from T star, such that from starting variable we should able to reach to, by applying this rules from P, we should able to reach to W, and W consists of only the terminals. W is having no variables. So, that means under this G we should able to reach W. So, all such strings if we collect, those strings are basically the collection of those strings is a language, because if we consider these as alphabet sets, it is a language, and then this language is called the language generated by this grammar G. Okay. Now, when we say a language is a context free language, suppose we have given a sigma, which is basically T, which is a input alphabet, finite set of input alphabet. Now, we take a language, we take some collection of the strings coming from this. Now, when we say this is a context free language, this L is called L is a context free language or in short it is called CFL. If we have a context free grammar which is generating this language, if there exists a context free grammar with the terminal as this, with some rules and the starting state such that the L of G is the L, then we say this is a context free language. Okay. This is the definition of a context free language. We should have at least one context free grammar. So, for a given language we can have more than one context free grammar. We will see that by example. Now, we will define what is called sentential form. Sentential form. Okay. So, we have given a context free grammar. So, this is yes. We have given a context free grammar. Now, alpha, which is a string, consists of some variables and some terminals. Okay. Now, alpha is called alpha is called in sentential form. This alpha is called a sentential form if alpha can be derived from S by the rule of this. So, if with one or more step alpha can be derived from S, then it is called. Alpha need not be a terminal, alpha may consist of variables also, but only thing the string alpha should be derived from the starting variable S with the rules of, with the productions of this G. Using the rules of P we should able to reach this, then it is called a sentential form. This alpha is called a sentential form. Okay. Now, we can define the equivalence of two grammar. When we say two grammar are equivalent, equivalent of grammar. Okay, we have given two grammar G1 and G2. So, we say these two grammar are equivalent if they are generating the same language. If the language of, then we say these two grammars are equivalent. So, we will take some example of the equivalence grammar. Okay, now let us take some example and we will see some language of that. So, let us take a grammar like this. Consider a context free grammar VTPS, where V is only having a variable S and T is the terminals for the alphabets, which is AB, and P the rules. So, we have these rules. S is going to ASB or S is going to the two rules AB. Okay. We can combine these two and we can write S is either this or AB. This is a grammar. This is a context free grammar. Now, we want to see we have to find the language generating by this grammar. Find L of G. We have to find the language which is generating by this grammar. So, what is the definition of L of G? L of G is nothing but set of all strings of terminals or alphabets such that which is derivable from the starting variable S, such that S should be reachable to, I mean this under G with the derivation of the rules productions P. Okay. So, we have to find this set L of G. So, what is L of G? Now, we will just see the S. So, our S is of the form ASB or AB. Okay. Now, from S what we can do? So, from S we can derive, we can either apply AB or we can apply this. So, if we apply ASB, then again if we apply this S ASB, so these are sentential form. So, ASBB. So, if you keep on apply this, how many times? N minus 1 times this. So, basically we are applying this production how many times? N minus 1 times. Then where we will reach? We will reach to a this a to the power n minus 1 S b to the power n minus 1. Okay. Now, then after reaching this, we just apply S is going to A b. So, if you do this, it will give us a to the power n b to the power n. So, a to the power n b to the power n is the sentential form. So, that means a to the power n b to the power n is derived from S for any n. If n is 1, that means we do not apply this rule, we will go for this rule. So, S is applying, this is applying 0 times. So, that means S is from, so this is the, okay. So that means a to the power n and b to the power n must belongs to L of G for all n greater than or equal to 1. Okay. So, L of G, all the possible a to the power n, b to the power n will be L of G. Now, the other way around we have to show that L of G is, to show this L of G is nothing but a to the power n, b to the power n for all n greater than this. So, this is a subset of this we have shown. Now, we have to prove this is a subset of this. That means, if we have to take any w from this, which is the terminal string of terminal which is derived from S, then we have to argue that w must be of this form. Why? Because our rules is like this. So, either we can apply this, S is going to ASB or AB. So, in any case it will be of this, this will be is the step like this. So, in any case w will be in this form a to the power m, sorry, w will be either of this form a to the power m, b to the power m. So, this way we can argue. So, that means this is a subset of this. So, eventually our L of G is this. Okay. So, this is accepting the language a to the power n, b to the power n. I mean this is generating the language a to the power n, b to the power n. But we know this is not a regular language. There is no finite automata which can accept this language, but we do have a context free grammar which is generating this language. Okay, so, we will take some more example. We will take few more examples. Yeah, so, suppose we take a find the context free grammar, find a context free grammar which is generating the following language, generating the language of even length palindromes. Even length palindromes. So, that means L will be of this form W W R, and W is belongs to the sigma is A B. Okay. So, so now how to generate it? So, we can take just S G to be the only, we can start with only one variable S, and then the alphabet terminals are just A B and P S. So, what are the rules? So, P is defined as S is going to A S A or B S A, sorry, B S B or epsilon, that is all. So, there are three productions are there in P. One is S is this is A S A, B S B or epsilon. Okay. And now we can easily verify that this is accepting this language W W R, the reverse of that. Okay. So, now we can take some more example. Some more example on this. So, we want to have a context free grammar for the regular language, for a regular language which is corresponding to the regular expression, which is corresponding to the regular expressions 0 0 star 1 1 star. Okay. So, this is our language. So, this is the regular expression. So, what is the corresponding language? It is 0 followed by any number of zeros, then followed by any number of ones. So, this is corresponding to the language 0 to the power I and 1 to the power j for any I j greater than 0, because this 0 is there, 1 is there. So, I j must be greater than or equal to 1. So, any number of 0. So, we have to, this is, we know this is regular, because this is we have a regular expression for this. So, this is regular. We do have a finite automata which can accept this language. Now, we want to find a context free grammar which can generate this language. So, any idea how to do? So, it consists of two language. One is this language, any number of zeros and then followed by any number of ones. So, it is a two part. So, what is the solution? So, the idea is the language is concatenation of the two language, one is this one, another one is this one. So, that is why we will form this grammar like this. So, we will start from a S C D, C D we will be using for having the two different language and the terminals are the input alphabets P S. Now, what is the rules? Yeah, so what is the rules? Rules are basically like this. S is going to C D. We use C for representing this zeros and D for representing the ones. So, now C is going to 0 C or 0 and D is going to 1 D or 1, that is all. So, this is our P, this is our productions. So, production consists of this. So, if you take any string of this form which can be, which is the sentential form of this grammar, any string of this form, say 0 to the power 2 and 1 to the power 3. How to get this? So, we will start with S, C D. Now, C is going to 0 C and D is going to 1 D. Now, this is again we need one. So, that is all. So, this C is going to 0 0 and 1 D. Now, again D is going to this, we have to have one more 1. So, we can again apply this. So, 0 0 1 sorry 1 1 D. Now, this is going to here. So, this is reachable form, this can be derived from this S. So, this is a sentential form, sentential form. So, any form of this 0 to the power I and 1 to the power j will be the corresponding language. Okay. Now, we want to complement this, we want to get a context free grammar which can complement this. So, we want to complement of this language 0 to the power I, 1 to the power j. Okay. So, complement means, so it will be not of the form zeros then followed by ones. So, there is no obvious way to find the complement in the context free grammar. So, we have to do some trial and error method. So, there are three cases. One case the string somewhere it is 0 again followed by 1 like this. So, this is the 0 1 in out of order, that is one possibilities, and other possibilities is we have only zeros string, and other possibilities is we have only 1 strings. So, that are complement. So, if you do that, so we want to find the complement of this. So, this will be like this yes, we need few variables for those A, B, C, D 0 1 P S. Okay, now we need to define the rules, so that we can reach to the complement of, we can generate the complement of this language. Okay, S is either A, B or C. Now, we are going to use this A, B, C for different purpose. So, A we are going to use for this all the string of 0 1 which is out of order means it is not that 0 followed by 1. So, for that we need to take D, A is going to D 1 0 D. Okay. So, this produces all strings with 0 and 1 out of order. And D is going to 0 D or 1 D or epsilon. So, it is either 0 string or 1 strings, but we have 0 1 over here. So, yeah, so that is the destroying that property, and B is going to 0 B or 0, this is the 0 string, and C is going to 1 C 1. Okay. So, this is the rules, this is the production by which we can get we can generate the language which is the complement of this language. Thank you.